We may now proceed with our next speaker. Again, in the interest of time, I will just say some 4 lines of our speakers. They have voluminous information for the CVs, but we don't have much time. So I'm very sorry if just say 4 lines. Our next speaker is Dr. Argel Bandala, a full professor of the Department of Electronics and Communication Engineering, De La Salle University. He is the 2020 NAST Outstanding Young Scientist. He was also the 2018 IEEE Asia Pacific Outstanding Volunteer. He is the founding chair of the Robotics and Automation Society of the Philippines, that is IEEE. And he is also the current chair of the Computational Intelligence Society of the Philippines, again in IEEE. He has published more than 155 Scopus Index papers. Ladies and gentlemen, I'm very proud to present to you Dr. Argel Bandala. Argel, you may go.
Yeah. Good morning, everyone. Can you see my PowerPoint?
Yeah.
Okay. So, unlike the previous presenters, I'm going to present a previous research done in our laboratory. And in behalf of my co-authors and research team, Aldrin, Ryan, and Erica, together with our co-faculty researchers, Engineer Maningo, Dr. Vicera, and Dr. Dajos, I'm going to present our research entitled Development of an Automated Cooperative Load Transport using multiple quadcopters. So here's the outline of the presentation. So I'll be discussing the inspiration of our research, how did we came up of this idea, and how the architecture of the system and the composition of and design of the algorithm, experiment setups, experiment results, and how did the algorithms performed. And then to end, I'm going to present some recommendations together with the conclusion. So, of course, delivery using drones are gaining popularity, especially now that we are facing a pandemic scenario, and wherein face-to-face delivery is of high risk of, or the delivery personals are of high risk in contracting the virus. So we are actually develop a system wherein will enhance the current scenario in drone delivery. So in Western countries, especially in the US and Europe, there are already existing technologies, drone technologies to autonomous delivery. So that's the inspiration of our research. And of course, if we are using drones, virtually we can go anywhere without worrying of the obstacles and other obstructions. However, there are several disadvantages in or improvements that can be done using drone delivery system. First of all, there are problems that we might encounter. So the image in the upper right is an oversized load. So basically, if you are going to use a drone similar to the previous slide, it is not that possible to have that drone deliver this package. So basically, if you increase in the current scenario, if you're going to increase the load or the package, it means that you need to increase also the size of the drone. And of course, there is this chance of failure. Most of the time, turbulence in air would mean loss of our investment or the drones. And then of course there's a need, of course, to address this probably we can do scalable systems to accommodate this disadvantages. So the research that we accomplish primarily aims to, of course, use or to explore the idea of using multiple drones instead of using a single drone to accommodate varying loads. So for this research, we we have a small scale system that is not capable of lifting 1 kilogram load, but by using multiple drones, we were able to do more than 1 kilogram lift. And then we aim to develop an algorithm that would make all of these drones cooperate to one another. And then, of course, we need to detect the load and to attach the drones autonomously into these packages. And then, of course, to implement a localization system so that we will be able to have these drones work cooperatively. So, oh, sorry. So what we are envisioning is to have this system to perform these specific advantages. So we are aiming to see that the advantage of scalability would downgrade the problem of big loads and oversized loads. And then risk reduction. When a robot would fail, probably the remaining robots would compensate for the loss. And this very you can introduce expansion by not increasing the size of the drones, but to increase the quantity and have them cooperatively transport a certain load. And of course, continuity. If the quadcopters would fail, probably a replacement drone can rescue or continue the mission. So we surveyed several existing researches, but there are several areas that lacks in application and needs to be improved. So basically, there are few researches on landing, stability, and the knowledge on these platforms. So for payload delivery, there are several researches existing, but several are tackling or at least a few would tackle cooperative load lift. So we are aiming to have an algorithm that would make this possible using multiple drones. So what are the considerations in our design? Of course, we need to locate the route as well as the origin and destination of the package. And then we are aiming to use a motion capture camera to perhaps mimic the function of GPS systems in outdoor to localize or to locate the position of each drones in the 3D space. And of course, the motion capture cameras will at least simulate or at least show how was the algorithm performs in terms of positioning and the trajectory execution. And then the operation, we since this is the first time we execute this kind of research, so we are confined in indoor scenarios in our lab to at least show the feasibility of this idea. Okay, so I'm going to present the flow chart and then how the drones are at least tailored fit for the application and what is the setup of our testing experiment. So basically we have the localization or the camera. We use OptiTrack. That's the first step, and then the positioning data will be transported or transmitted to our computer, and then a software called Motive would iterate the position of the drones in 3D space, and then our second computer would control the positioning as well as the trajectory generation of each drones. So we have here our remote testing room. So we have an improvised lab for this research. So it requires a lot of space. So as what you can see, we have our cameras here. We have 6 sets that would basically observe the robots and its positioning. So the other 2 is in the other side. And then this is our capture volume, or the 3D space, or the operation where the robots would execute the algorithm. And from our previous research, we are doing previous algorithm testing. So we have here an open source drone, and we modified it to at least control a bigger drone with the green propellers, as what you can see here. And of course, here is the central station. So basically, all of the camera images or camera data will be fed to this hub, and which converts the positioning data and transmits it to the computer. So here's the concept of, or an animation of how we intend to do this research at that time. So basically, we have markers placed on each drones, as well as the attachment or where the robot will attach the load. So in our software, the drones on the lower left is at least represented by this rigid body, and the attachment or the placement of the hooks are placed in the circles on your right and in the middle. So basically, the drone would fly and attach to itself in that position. So we have here, we have here our first, we have here our first test. So basically, the yellow circles is the representation of the drone in 3D space. Well, at least in our algorithm. Yeah. So the idea is to have specific points that would that will serve as the attaching point, or the point of contact with the load and the drone. So yeah, we use an open source drone. So we worked on in previous researches, so we are very knowledgeable on at least the functions of this drone. So we have a converter that would control, or will use this drones to control a bigger drone. So here is the adapter and how it is laid out in the bigger drone. So the algorithm flowchart would be, of course, the information or the position data will be fed in our computer, and then a software called Motive and NatNet would converts this data into position information, and a ZMQ server would convert the information so that the information will be ready for processing of our controller for the drones. So we utilize a basic PID controller for processing the coordinates and the orientation of the drones for movement and the trajectory planning. So I will skip the math. So yeah. So basically, the first step would be operating the drone into a hover mode, and then inserting the hook or latching itself into the load. Then, of course, the final step would be execution of the trajectory as well as transport of the load. So for position checking, we utilize this algorithm, so I will not discuss in detail. So let me show you how we tested the system. So basically, we measured the orientation, so that's the pitch, roll, and thrust, as well as the 3D positioning of the drones. So first would be the roll test. It is the sideways movement of the robot from left to right. So here are the data that we collected. So basically, we have tolerance for the position, and the green columns represent how many times did the robot cross the boundaries, and the yellow column represents the units of movement. So we summarize it as movements is in units per minute, and we have here the graph of the movement. So basically, we gave commands in the robot to move at certain position, and here's our results. Same with the pitch test. It is the backward and forward movement. So as well as the errors and the movement in units are measured. So here's the results. For the thrust or the altitude, we measured it same way. So here are our results. And this is the graph of the altitude. So for the delivery test, the idea is to have a scalable system. So we will start at a single drone, and then it will attach to itself, or will attach to the load itself, and it will measure if the weight of the load by actually measuring the altitude or the thrust it generates before a change in height or altitude is observed. So basically, the drone individually tests whether if it can lift the load. If the maximum allowable thrust is reached and there is no change in altitude, it will at least send a message to another drone telling it that that the first drone needs to have a support or help from another drone, and then the process is done in loop in loop. So we actually tested until 3 drones. We tried 4 drones, but the space actually is not enough. So, but we proved that we can do at least up to 3, and we are capable of increasing the number of drones. So, yeah, for the single drone test, we have a single load, and we intended to have this drone transport the load from a point to another, and then to latch itself, to lift the lever and attach itself to the load. And we had 80% success. Well, we had a target position, and 80% of the time the load is inside that target position. So we measure the time of unlatching, total time, transport time, and the drop accuracy or the exactness of dropping the load. So here's the summary of our test. Note we've done a 4-meter movement from the origin to the target point. So I have here the trajectory generated by single drone. And then it is done, the same test is done for 2 drones. So here's the result. So I have here the summary. So we actually gathered separate trajectory data. So The actual position, if you can observe, is a difference of certain distance from one another. That is actually the distance between the latching points. And for three robot or three drone setup, we've done the same. So here's the result. So well, we actually observed that increasing the number of drones would actually increase the accuracy of drop. So if you can see, our drop accuracy is around or more than 90%. And here is the summary of the movement and time. And this is the actual trajectory that the drones made for a three drone transport. As a conclusion, we successfully tracked and directed the route of drones through motion capture cameras. And we actually automated the control of drones in different destinations from one point to another. And augmentation of latching process using magnets and a hook was actually implemented. The latching and unlatching process actually took around a minute, and the drones performed balancing lift. Basically, each drones compensate for the errors in movement of the other. In total, they actually have a balance lift of the load. And of course, we have around 80 to 85% of the delivery accuracy. So basically, a certain point is drawn in the target point, and we measured whether if the load is inside that area or not. And then actually, what I've mentioned earlier, there's an improved accuracy and increasing the number of drones. So some of our contributions would, of course, we have displayed precision in movement using motion capture cameras. And the small drone actually was the ability of the small drone to control a bigger drone using the facility of the open source robot was displayed. And we actually demonstrated integration of the swarm technology in delivery of payload. So some of the recommendations that we've seen throughout the course of the research is improvement. We need to improve further the hover stability or the load transport stability when implementing it in outdoor scenarios. So we have an ongoing research of payload stability algorithm development for this application. And of course, we need to improve the resistance of drones, each drone for propeller wash. By, of course, this is related for in our first recommendation. Of course, the stability and resilience in external forces. So I have here a video demonstrate. I have here a video demonstration of our research. So on the upper left, you have here a single drone transport. So as what can you see, the load tends to swing. Actually, that contributes to the error. And then on the upper right, we have here a two drone transport, and at the bottom we have a three drone transport test. Yeah. I would like to end my presentation. In behalf of my co-authors, Aldrin, Ryan, Raf, Erica, and my co-faculty researchers, Martin, Doc Ryan, and Doc Elmer. Thank you for listening.
All right. Thank you very much, Argel, for that presentation.